So welcome everyone to the Hyperloop seminar to the spring semester. So this is already our second last edition. Yes, but I'm happy to see a lot of faces. So just to start, I have a few points to say, so we are all settled to start. So just for people who are maybe new to our seminar, so what we usually do, we have the talk, the presentation, and during that presentation, you can use the Q&A button on Zoom. So this is right next to the chat button. And there you can put in all of your questions so that when the presentation is over, we have an overview and we can go through all of those questions. You can also send them anonymously if you want to, and you can also upload other questions. Yes, so sometimes you can, if we have time, we can also answer questions through the microphone, but it's easier if we have an overview and all of the questions in the Zoom icon. And also, so I already talked about this a little bit. So we have our YouTube channel where we have all of our past seminars uploaded. So you can go there and check it out. And yes, as I said, so tonight I will upload the first 3 talks of this semester, and all of the other years are already uploaded. And also we have a database. So all of our talks, we have basically listed down and you can check them out. If there is a paper, we have also linked the paper, and we have also linked the link to the YouTube video. So, and I think with that, we are settled with all of the informations and we can already start with our first talk. Yes, exactly. So we have 2 presenters, Peter and Daniel. And for the introduction for our guests, I would give the word to Lucas.
Thanks. And I would like to say it's very welcome to see this presentation today. We haven't seen many presentations of ourselves, what we have done as the hosts and members of the Hyperloop seminar, to see what we've developed recently and lately. So I'm very, very interested in what you're going to tell us today about the vacuum applications you have developed, to look back at what has been the case in vacuum technologies since now, and then also giving us an outlook of what you're going to do right now. And yeah, as said, Peter Woodward, so it's nice to see you working together with the research team at Eurotube. And I think let's have a look at what you've done together. And the word over to you too, and there you go.
Thank you.
Thank you very much, Lucas. Then with this said, I will share the screen. Now you should be able to see it. So thanks for the brief introduction. As briefly mentioned, today I have the pleasure to present alongside Peter Woodward, CEO and founder of Utilities Valves, the valve development Eurotube has been conducting in the last year to came up with a valve design, which is now standing in our demo tube here in Dübendorf. So the objective of today's presentation is to give you more detail into what this development has been looking like, where we came from, and how this translates into further steps of large valve, scalable valve design for Hyperloop applications. To give a bit of an insight on the agenda, we will be going through a short introduction on utilities valves per se, where the company has its roots from, what is the core business, core strengths, technologies, before we then jumped into the design brief of large-scale Hyperloop valves, where we, or Peter is shortly highlighting what is the current state of the art of such large-scale Hyperloop valves, and what are the challenges which brought to the design of the current valve we developed together. Then in chapter 3, we will be detailing more on the technical side, specifications to the 1 to 2 size valve we co-developed, and then in chapter 4, we will be giving more insights into testing and validation of the valve which has been developed. Last but not least, we will give a short outlook on conclusions and where this development is going to lead us to. So with this said, Peter, I would hand in the word to you.
Thank you. Good afternoon, everybody, and thank you very much for joining us today to share our experiences in developing this large-scale Hyperloop valve, which has certainly been a challenge. And I think that there's one or two other companies out there in the world that have tackled the same developments, and it's not for the faint-hearted. And there's some very interesting things to overcome. I'd like to start with some background on UV, so you can see where we're coming from, and that will be followed by a PowerPoint presentation to share with you the breadth of product range which we've been handling, which goes from very small diameter to extremely large and high pressure valves. Well, it's the large end where we've had a lot of specialization. We're not going to talk very much about that. We're going to get through it to give you a strong visual impression, but it's quite relevant. This is why I wanted to do it, because on our journey, we have created some interesting technologies. Some have been patented. And as it happens, some of those technologies will spill over into, or have spilled over, in fact, into what we've been doing with our Hyperloop development. So we're specializing in particularly large valve design and manufacture. We just show you the key management team of 13 people, with a very large manufacturing resource behind us. You can just see from the titles here that we're covering technical development with very good chief engineer, with Sonny Ewan, who I've worked with for over 16 years now. He and I tend to head the design and development. We have a good QA director, and also a director of operations. So these guys are very experienced in the production processes which we bring to bear across our business, an FD, and you can see the rest of the team. And we have people resident in China and in India. So we have an underground team, and of course we're visiting them and working with them on a very regular basis. So that's the team, and if we just look at the core strengths, which I've touched upon, but the industries which we're specializing in are water supply and hydropower, and water irrigation for the main part. And this takes us very much into the large valve technology and the high pressures, and also challenges us for sealing solutions. So I think we should go to the PowerPoint presentation, and as we go through this, please look out for the word seal when you see it in red, because what this signifies is that within the product you're looking at is some highly relevant technology which we have developed and is part of our history and experience on what we're able to carry forward and put into our think tank for the solutions for this very large scale vacuum valve that's never been tackled before. We'll just stop on this one. This seal is about the back seal, and we'll be talking about that later. But just to observe here, the bronze nut is actually you see in the bottom left-hand corner It's an O-ring gland seal that's sealing the stem, the stainless steel stem. And of course, O-rings eventually do need to be replaced. What we've got here is a design where we can back seal the valve. There's a device inside the valve where we can back seal it and completely remove this O-ring gland. And if you look at the bottom right-hand corner, you'll see it's completely dry, but it's actually under 30 bars water pressure. We've successfully proven the same technology, or varied the technology and carried it forward into Hyperloop to achieve the same complete isolation on the stem from inside the valve, so we can remove and maintain in the long term the stem sealing without interruption to service, with the pipeline still open under full vacuum. This valve here is the largest spherical valve in the world. We didn't make this, but we have the technology. There is a secondary seal here. It's on very high pressure turbine isolation on hydropower. So again, it's contributed very much to our thinking. Large diameter butterfly valves is where we have also developed special sealing. And as we go forward with the slides, here we see this is a 25 bar valve. Here's a project which was 34 valves, 4 meters diameter, complete with the hydraulic power pack unit controls for a large irrigation project in India. And if we just pause for a moment, this is highly relevant. We developed and patented a seal technology for these very large butterfly valves. And if you look at the edge of the disc here, you'll see 2 different types of seal. This allows man entry into the pipeline against the full static head of water, the other side of the valve. So high security isolation, very much part of our theme, and of course extremely important for Hyperloop. There's a large project for the Middle East in Kuwait we completed last year. A very large number of valves indeed, and all of that has brought us to Hyperloop. So thank you for your attention for that. So let's look at the initial design brief that we agreed with Eurotube. This impressive valve produced by GMB in partnership with Hyperloop TT, I believe is 5 meters diameter. It's essentially a knife gate valve, horizontally installed at this size, and it's I think a very good valve, and it adopts a different sealing technology from what I can deduce from what they allow me to see, to the way we have approached it, and there's nothing wrong with that. But before we go any further, for those of you that are not necessarily completely familiar with, and we'll call it a knife gate valve, because essentially that's where it stems from, but it's become really a valve in its own right as a Hyperloop valve now. But just as we talk forward in this presentation, we'll refer to certain things. So if we just quickly familiarize, the main body is the center section, and it has a top bonnet, flange to it and a bottom bonnet at the bottom. The bottom bonnet is allowing us to, through an access door, remove the accumulation of debris in the long term that may build up, dust and silt. So we have a clean out chamber at the bottom. Can we go back to that one, please? We'll see at the top there on the right-hand side reference to the stem gland seal, which I've already commented on in the other presentation. And outside of the top of the bonnet, you'll see that that's where that is located. But inside the bonnet, if we look to extreme right, we see back seal. And that is a special seal we've designed. So when the disc is in the fully open position, as is shown there, this creates a back seal, and the whole top works can be removed under full vacuum. There's a table you can refer to later just to understand the materials that we've used. Essentially, it's carbon steel of a high grade. You can see the strengths there, epoxy coated, but where we need good sealing surfaces, of course, for vacuum, it's stainless steel, which is what the disc is made of. We can apply different grades of material, look into the future, but this was relevant for the demo tube at the moment. But longevity and ease of maintenance or zero maintenance is one of our goals. So looking more closely at the detail of the design brief, at the top here, we see the differential pressure of 1 bar. 1 bar atmosphere to 1 millibar vacuum is the objective, and it requires a tight shut-off as a safety valve and a low maintenance. We know that very few manufacturers have shown interest or even the capability to develop such large size vacuum valves. And what we note next is that the vacuum valve industry generally is made up of small valves up to 1 meter diameter, and essentially for hygienic non-particle clean room environments. So with our valve, that's not a requirement, and could have been misleading, but having understood we can forget that, it made our task a lot easier, but we still have to achieve the vacuum isolation down to 1 millibar, but not ultra high vacuum. So there's a number of issues to overcome, and the ones we're highlighting at the moment here to comment are the most difficult and most important. The horizontal forces, which are typical for Hyperloop valves, and the DN 2.2 meter now, which is the one we have developed so far, it's 40 tons horizontal force acting on the door, even though it's only 1 bar differential pressure. The surface area provides that sort of force. And as you go up in size, you can see the corresponding much higher forces involved. Now, we see under point 2 here that this causes the axial disc displacement downstream, and this means that the upstream seal on a two-sided valve, a bidirectional or bi-seal valve, the upstream seal will decompress and the downstream seal will overcompress. And it's very important to control both of those things. It's quite normal with gate valves and knife gate valves in the normal way to only seal on the downstream face with the additional sealing force. But but we've developed valves previously where we've met this challenge of wedge displacement horizontally, and we've tasked ourselves with maintaining the inlet seal or the upstream seal tightness as well. And that's what we set out to achieve here, and we have. If we drop down to the lower emboldened bullets, vacuum sealing we've just talked about under high horizontal forces, but the body and disc flex distortion at these forces will cause leakage even for high pressure fluid valves, such as these large butterfly valves and big gate valves that we've done before. And of course, much more difficult for vacuum air sealing. We'll have a look in a moment at the FEA analysis and the distortions that are created. But bodies and discs will flex. And we have always aimed for 100% seat tightness for fluid valves under the highest pressures going up to 40 bars. But it is a question of avoiding the distortion and flex, which of course would upset the sealing. And with vacuum, it's more sensitive. The next point is the disc axial and lateral guiding is important. We on the lateral guiding, we must be sure that the disc is brought down centrally. But most importantly is the axial guiding with this high differential pressure. You cannot impose tight guiding. Let's say we can get down to 1 millimeter or maybe 2 before you run into other problems of thermal expansion or dust or grit or deposits, which then foul the guides and the valve becomes inoperable. So there are limits, practical restrictions on the guide tolerance. But what we really want here is to control the overcompression of the downstream seat and also control the degree of upstream seal decompression. So we've looked very closely at how to achieve that with a different approach to guiding, which has been successful. So our main focus in designing this valve has been really the attributes of seal design and to achieve an optimum sealing compression, both upstream and downstream, to vacuum-proof sealing surfaces. And that's the surface of the rubber itself, as well as the mating disc, which has to be polished to a very high degree, because otherwise vacuum will pass. Of course, operational security with such valves is extremely important. And as with any product, there are a number of failure modes, and we need to consider all of those and what the weak links are, and then eliminate them. One of the issues is, of course, the actual sealing itself, because there are different possibilities depending on which philosophy of seal and seal activation that you adopt. So in the end, we took an approach which has actually married 2 types of sealing together, where if one type of seal fails, the second one, which is different in its technology, will not be exposed to the same failure. We call it a belt and braces approach, which I think you might know the term of how to keep your trousers up using braces and belts, and it's a good thing sometimes. Finally, the whole question of maintenance. You see, with such big valves, we can't be putting these valves in and then expecting to remove them from the pipeline or break them down or strip them down for maintenance or failure repair. These valves should be designed for zero maintenance, and they certainly will have a very long life with very high cycles. But there comes a time where certain components will require attention, and what we need to do is to either resolve that component refurbishment with no interruption to service, which means the pipeline or the tunnel is still open, it's still under full vacuum, and repair can take place or refurbishment can take place. And second to that, we may have to carry out certain long-term planned maintenance in very short shutdown periods. Maybe it's at night or at some suitable time where we can isolate the valve away from vacuum and allow a maintenance to take place. But the way we need to do that is without stripping the valve down and having heavy lifting equipment. So we've designed, everything we've done is very much in mind of maintaining the valve in situ, even with man entry into the valve under safe conditions, to carry out, for example, seal replacement, which can be done inside in about 4 hours shutdown to completely replace the seals. And we've designed the seals in the valve in such a way that they are retained and can be broken down. The retaining rings are, for example, in segments of 4, which are easily lifted by one person, and you can dismantle the valve from the inside, replace the seal, and put it back into service in short time. So our bringing together of our background and what together with what Eurotube wanted to achieve, we agreed upon a set of objectives to team up, and here they are. We wanted to validate the Hyperloop technologies. It would have to be a custom designed valve, and Eurotube also wanted to have rail bridging concepts across the valve, if necessary, within the valve body. And that's all possible if they need to do that. And to prove the technology based on the demo pipeline with a 2.2 meter diameter valve, but everything we did from the very beginning was aimed at full scale as well. It had to be scalable solutions, and so we designed a 2.2 and a 4.4 side by side. But the first valve manufactured is 2.2, but all the technologies are scalable. So we know that from what we've achieved previously in other valve designs and developments. So we're confident that whether it's a 4.4 or a 5.5 or a 6 meter valve, it will achieve the same result. This is a summary of the final valve results that we've achieved. So 2.2 meter vacuum valve. I think it's fair to say it has been radical technology that has come out of this teamwork, and scalable up, we'll say, to DN 6 meters, but it's not limited at that. We have this high security unique sealing system, which I've touched on earlier, and involves different technologies combined to give us additional security and offset specific failure modes that may occur in the future, or wear factors, which will be different. This valve we've now manufactured is 13 meters high, and suitable for vertical installation. If we go to the next size up, it will have to be horizontally mounted, but it doesn't affect any of the key technology that we've now developed. It will require that the valve is supported on its bottom edge and guided on the other side of the valve. And we will be looking at how to have a rail system for the valve to slide backwards and forwards of, which is basically wear resistant and doesn't need replacing. But we will also look at any inline maintenance that may be required as part of the study going forwards. Design force we've mentioned earlier. Here we've got 45 tons acting on the door with a design pressure of 1 millibar and a differential pressure of 1 bar under pressure vacuum. So let's have a look at some of the design insights. As I mentioned, the strength analysis modeling, FEA modeling on the body and the disc is extremely important in any valve design. And what we're really aiming for here, though, is far more than strength. The valve is more than strong enough. The most important thing is to achieve the minimal distortion or flex. So it's about rigidity. Here we see on the body that the maximum displacement is actually only 3.4 millimeters, which is on the rib ends, but the sealing area, which is the critical part, is only 0.04 millimeters, which is very, very small. Which means that the seat is not moving away from the seal to any degree that would upset the sealing, and this rigidity is most important. If we look at the disc, the next slide for the disc, there we are. So it's the same. It's exactly the same criteria, but here in the middle of the wedge, we've got 0.5 millimeter distortion, but at the edge of the disc, in the sealing area, we're down to 0.1 millimeter. So altogether, between the two components, a remarkable level of rigidity, given the forces that are involved, and that will scale up as the forces get larger. It just means more material, more thickness. The disc is made of two plates, which are reinforced with internal ribbing to give it again the rigidity. So it's not just about the thickness of the plate material; it's also about the internal bracing that takes place, and that's worked very well. We've got other areas of sealing. The stem back seal, the stem O-rings, as we've said, are replaceable with the valve fully open under full vacuum, no service interruption. When we consider that this is the only seal which is a movable or rotating seal, with the disc rotating, going from the inside to the outside atmosphere, it's commonly accepted this is the most difficult seal to achieve, particularly for vacuum. As long-term wear takes place, and we've got a 3 O-ring seal, so the one in the middle is under perfect conditions. So it's very long-term service here, but there will come a day when it needs replacing, and there will be a lot of valves in service ultimately, and so planned maintenance without disruption is very important. A lot of operational benefits can come out of this. Disc seal, as we mentioned earlier, regardless of the horizontal forces, and it can be from both sides, so bidirectional. Upstream and downstream seals are both simultaneously vacuum tight, truly bidirectional valve. And then we've got the added security seal, which we may or may not need to use or choose to use. But if we need higher levels of security, we can engage this seal to provide a higher level of security. And as I mentioned earlier, it's a different failure mode and different wear factors. So this double seal approach works very well. Disc guiding. The lateral guide is easy. The axial guide, we have developed a means of controlling the compression on the downstream face, irrespective of the fact that the wedge still wants to move. We have what we call a seal guard, which is an outer ring of PTFE, which acts as a guide, and it also acts as a guard because it's outside the main seal area circumferentially, and it prevents ingress as well into that area. It is a low coefficient of friction, so the guide is acting in a way that keeps the operating torques as low as possible. But also importantly, because we're guiding the sealing face all the way around, it prevents what we call disc cant. If the disc is to cant over a little, and we're talking 1 or 2 millimeters is a lot, that would upset the seal. So it is perfectly flatly guided without any disc cant, and we're talking about large discs here. Stem over in bush, we've already covered that. Replacement under vacuum. Stem nuts, we're using a rotating stem with a nut. The nut's embedded in the top of the wedge. It's a non-rising stem, so as the actuator on the top rotates the stem, the nut rides up the stem and takes the disc up with it. The stem nut is doing a lot of work. The stem itself is not, because of the length of the threading over the full length of the stem. We have arranged this valve that the stem nut can be replaced under vacuum with the valve in the shut position. So you'd have to interrupt the service, but it's a very quick change, and we have access through access doors to achieve that. Then there's other sliding components where we've talked about guide rings, the seals themselves, replaceable in situ from the inside with the disc in the open position, with man entry, but you need to isolate the vacuum either side of the valve. But it's a short shutdown of maybe 4 hours to effect that seal replacement. We're talking very long term here, by the way. And then actuation, the gearbox itself, little or no maintenance required. And if we look at the wear factors, we tried to grade these at the bottom. You can see nearly everything is minor degradation, which really means nothing to worry about, not expected to be replaced, or we have the minimal long-term wear, which is about the actual seals themselves. And then stem nuts, they will require replacing at very long intervals, but it can be planned maintenance, and it's a very quick change. And if we turn to hydraulic actuation later with horizontally mounted valves that you might want to operate more quickly, or they can still be electrically actuated, then we can forget about the stem nut. Then it will be a cylinder and piston rod. Okay. Materials used for rubbers. We're going to show you this video whilst I'm just talking this through. You may know this is calendarizing calendaring process, which is part of a process used for formulating compounds of rubber. It gives us the ability to change the mix, and the reduced friction and seal wear that can come out of an improved formula, and also a good surface finish to optimize the sealing performance is why we do this. This high compression that we're achieving here in the calendaring process adds very much to the abrasion resistance of the rubber as well. We go to the next slide. So just a few more comments on the rubber, because rubber technology in most of our products is extremely important and key to elevating its performance. Standard rubbers, take a standard MBR, it would go through stage 1 intermixer and would come out as a standard product. And if we go to stage 2 in calendaring with 2 open rollers, this gives us a very even disbursement of the chemicals. You can see the key bullets below what we achieve by applying this heat and high pressure to the rubber and customizing it to suit our objective. We get the equal chemicals dispersion, but we get a lot of increased strength from compressing the rubber, and also this smooth, silky texture, which is perfect for vacuum sealing, reduced friction, and low abrasion resistance. Okay. We've just adopted the standard practice of vacuum flanging. Needs to be stainless steel to stainless steel flange face and companion flange, but we have increased from the normal 1 to 2 O-rings for additional safety, and moving on to the choice of actuator, we went with Elmeua. At the moment, this has been designed to achieve 6 minutes, but we can reduce this to lower with electrical actuation by sizing the gearbox and actuator differently. We can probably get that down to somewhere in the region of 2 minutes, but we can get to probably 30 seconds with hydraulic ram actuation. This is all for the future to be decided.
Thanks, Peter. With this said, we jump over to testing and validation, especially to see how these design insights translate into vacuum performance. To give you just an overview for those who are not that familiar with vacuum, the way we measure leakage is through the volumetric leakage mass flow, which you can see in the image. We are calculating the difference of pressure over time applied to a certain volume. This formula, or specifically this pressurized measurement, is following a European recognized norm. And as you can see in the image, the process is the following. From 1000 millibars, which translates into 1 millibar, we are pumping down up to the desired target pressure of 1 millibar or beneath. When we arrive to 0.2, the test object, in this case the valve, gets isolated with means of a check valve. We are isolating the volume which is trapped, the vacuum which is trapped in the valve. And once this happens, we start a recording. We see a pressure rise, and then through the continuous pressure rise over time, we then evaluate the leakage obtained through the valve. This is the way we assess internally the vacuum performance of the valve. If we move forward to the testing equipment we used to compute these performance values, we denote the use of vacuum-rated ISO-KF flange connections, as you can see in the image. We also make use of pressure sensors, also the ones we use internally in our lab to conduct research, and then vacuum-rated check valves. As you can see in the image, the way we measured vacuum now specifically on site 2 is flanging a pressure sensor to a check valve, which is then trapping the volume once we close the check valve. If we have a look to the testing matrix, here you can see some of the tests we have been conducting. This test campaign has been going over 2 weeks. And here in a nutshell, we are clustering the most relevant tests. So for you to know, we cover tests on the body on the body level, meaning once the gate is removed, so to evaluate how the body is performing, not only under overpressure, but also under pressure. And then we evaluated the vacuum performance of the seal, method, disc, and security once the gate is closed. So here what you can see is we also evaluated the vacuum performance of both seals methods once the gate is closed. For that, we attached 2 end caps on both sides, under which then we put a vacuum and regarded the pressurized test. Here in a nutshell, you can see the test results. We took the liberty to cluster the most significant ones, which are reflecting the vacuum performance of the valve. Regarding the body test, we obtained a pressurized test of roughly 4 millibars after 20 hours, which is quite remarkable. And looking at the seal methods for disc and security seals, we are even in a lower range. So overall, what we can say after the test conducted is that according to our internal requirements, the valve passed the vacuum tests, which are certifying the valve for operation and further scalability of these valves for commercial Hyperloop valves. And now the next step will be to validate the integration of the valve into the full infrastructure in demo tube. So now looking into future directions and conclusions, we can say overall that based on the design insights we saw and the performance values we measured through the vacuum tests, the valve is certified and eligible for an application in full infrastructure Hyperloop lines. This valve is, as mentioned before, going to be validated now as a full air locking system in demo tube. And as part of the European Hyperloop landscape, Eurotube, as part of the Hyperloop development program, also enables then in this extent UV to get insights now into valve design and further developments, which is enabling, in this case, strong partners in large-scale valve manufacturing to bring in their ideas. And just to briefly mention from my side, in case there is also interest from other organizations to open up discussions with both Eurotube and utilities valves, we are open for it. So in case there is interest, don't hesitate to come either to Peter or me. Peter, for this, I would also leave the floor to you.
Yep, thank you. Yep. So on item 2 here, we've we have we believe we've got good added value for this Hyperloop community, but this is only the beginning, and I think now very close to this technology of Hyperloop valves. There's other milestones we can achieve, but right now we have a patent application in process now, so we are protected for a long time ahead. And in fact, there are 6 areas within the valve design which would justify this application, and even the combination of some of those features working together. So moving forward, back to you, please, Daniel.
As I briefly mentioned as well, as part of the Hyperloop development program, we are giving the chance here in this case to UV to extend their involvement in the European landscape. This is quite a significant milestone, since you might have known from social media, the European Hyperloop cluster is now growing, not only through our colleagues in Groningen, but also through the research infrastructures now here in Switzerland. So thanks to the involvement of utilities valves, we have a big know-how gained in large valve manufacturing designs, which is then enabling us to look into this topic much more in detail for the coming years to come.
Yeah, I think that on the last item there, the future valve development, this is an interesting next step, because I would expect that the next valve that we'll be looking at will be larger. We will look at the best solution for horizontal actuation, which will have quite a lot of advantages in some ways, but there are wear factors and maintenance considerations, and we want to basically zero those out. And I think we will. We have some ideas on that, and we do have some experience in very large horizontally mounted valves, which are used in flue gas applications at high temperature. They're big valves. We'll be looking at actuation types, how to arrange this with the valve horizontally. Almost certainly hydraulic actuation will become an option, and we need to think about the solutions for valves on the network which are far away, and those which are in docking stations where a higher level of operation and maybe a higher level of speed of operation. So depending on the equipment and the valve performance that's required will also have an influence. So it's good to have these options available, and all of these are fairly straightforward side of the valve for us. Lastly, optional seals technology, and we are very pleased with what we've achieved so far, but actually we have 1 or 2 other things in our mind which would not replace but could present alternative solutions depending on what the environment or the actual location or application might be. But we will still take a belt and braces approach to the safety valve security. Thank you. So here's some contact details for Daniel and myself, and please feel free to ask any further questions or show any other areas of interest. We are here and highly interested to develop this further. Thank you very much for your attendance today.
Yes, thank you, Peter, and thanks, Daniel, for the presentation. We actually do have some questions from
Yes.
the audience.
Mhm.
And yeah, I think I will just start from the top. So one is about maintenance and also further development. So how did you solve the challenge of maintenance? And what are possible further development ideas you have for this?
For maintenance, did you say?
Yes.
Yeah. Yes. To summarize some of what I have mentioned, we've identified the components which are susceptible to wear or damage, and how to access those components through inspection chambers, which are provided in the valve body, and then which of those items can be replaced with the valve in service without disruption to service, because this is the prime objective is to maintain the valve with the tunnel open and the service running. Not always possible, but then you go to the next level, which is how short the maintenance can be. But most importantly, what you must avoid is dismantling the valve or even valve removal. It's out of the question. Once it's in, it's in. That's it for life. It's got to be maintained. It's too heavy, too costly, inaccessible, heavy cranage. So within our valve, everything you look at is either zero or very minimal maintenance in short time. Some of it, which I've already highlighted, can be done without interruption of service. And the balance, there's not much to go wrong here, the balance of it will be very short replacement interval, which could be arranged on just normal downtime if the system's not running at night or whatever. So we've carried forward quite a bit of experience from the past, because on very big pipelines that we're involved in, we're building some valves in India at 4.6 meters diameter at the moment. These big pipelines, they don't want to dewater them. They basically want to carry out maintenance with safe, secure seal isolation for man entry and work from one side of the valve to refurbish and maintain it, and then go back into service. It's the same as you losing your vacuum on a rail system, or you've got people you need to evacuate because there's a problem on the tunnel, and you need to isolate two valves on the network and safely take people out. So the security is combined with the maintenance. It's very interrelated. And maintenance should be planned maintenance, no surprises, and should be short or zeroed.
All right, thank you. I think that gives us a nice overview. So in general, you could already profit from experience.
Very much
nice. So. Okay. So then maybe one more specific question from SEC. I think it's about the Eurotube valve. So what is the approximate cost per valve? If you can say that.
Okay, closely guarded secret between our special support to Eurotube and ourselves. But on the commercial market, we know from earlier investigations that such a valve, if we talk about full scale for the moment, a full scale valve, 4.5 to 5.5 meters, I would not be surprised to find a market price in the region of 750 to $1.2 million, 750,000 to $1.2 million. The reality for me is we can do a lot better than that, but we can't reveal that. And we are in a comfort zone now with Eurotube, and they're very comfortable with it indeed. But we know by comparison to other options which have been considered, there's a very, very wide stretch. I would say the bottom end of the market for such a size of valve is you wouldn't get it under $500,000. And you'd have to, I don't even know that that's quite possible, but in that region, okay. So it's quite a stretch, isn't it? I think that capacity is another question which comes to mind, because once commercialization starts, these are big valves. They take a while to build, even if the technology is already proven, and therefore manufacturing capacity is extremely important. But the way we build these valves is very efficient, on time, and it's cost effective, therefore, on time and cost. So I'm very optimistic that we can set the pace here.
Nice. That's good to hear. And then maybe let's just do one last question. So you were already talking a bit about improvements, and one question specifically is, are there certain parts you still want to address to make the design more safe for passenger transport?
Yes, there are. I think safety we've got. What I'd like to do is to improve the longevity of the valve and pursue zero maintenance, or so far into the future that we can get operating cycles to a real extreme. I think we're good now, but I think that there are other alternative sealing solutions. One of them's in the valve now, which is zero maintenance, but there's other ways of doing it. But then you have to ask yourself, and I can't speak too freely at the moment because we're in a patent process, but one thing that's important is that one type of seal requires activation, but the seal is virtually zero maintenance in terms of wear factor. But then if the activation of the seal failed, not meaning the seal failed, but the actuation or activation means failed, you've actually got a valve which you can't operate, you can't seal. So the alternative in the belt and braces approach is to have another type of seal, which we've got, and it's very successful, where there is contact with the seal, but we do it in such a way that the wear factor, again, is very low, but it's not zero. But that seal will always operate. And the only thing you need to do is move the disc up and down.
Okay. Yeah, sounds nice. So I guess we have to be patient until we can actually see this valve. Yeah,
we've got the protection now, but we've got 18 months in which we can adjust the claims within the patent application. So it's not that we can't disclose it, but we can sign confidentiality agreements which allow then us to be more open with future partners or people of interest, and share like we share with Eurotube everything.
Yeah, makes sense. All right, so with that, I think we would close the Q&A as we are already a bit past the time. Thanks a lot, Peter, and thanks again, Daniel, for your presentation.
You're very welcome.
You're welcome
for hosting us.
Nice. Yes, so just a few closing words today. So we are gonna have this talk also on YouTube, and I hope to see lots of you again. And I wish you a nice evening.
Thank you very
Bye,
much.
everyone.
Thank you very much.
Bye-bye.
See you next time.